Okay, computer froze, trying to get back online. Hopefully this is going to work. Okay, so we were talking about a t distribution as a distribution of the uncertainty of the mean. So here's the idea. We measure a sample mean. So for example, we measure the average discharge of the average annual discharge for the last 20 years out of the lock saw. And we have this measurement X bar, which is the mean sample all right, and so this might be, for example, annual discharge. All right, so we have this sample, and there's some probability distribution. All right, so here's X bar. This is our sample mean. And we know that the farther away, like the idea that we could measure a sample mean and it's really, really different than the true mean, it gets less and less likely. So the farther I am away from this sample mean, I know it's less and less likely that my true mean is this far away from my sample mean. You know, at some level, my sample mean is not going to be infinitely far away from my true mean. So the idea here is to put boundaries or confidence intervals on my estimate of the mean. I'm going to say, I'm pretty sure, according to this t distribution, that I have a 95% chance that my true mean falls within these two bars of my sample mean. So my 95% confidence intervals are two levels out here. All right. And the idea is that 95% of the time, I would expect that my sample mean falls within these two bars of my true mean. All right, so I can use the t distribution and my standard area to calculate my confidence intervals. C sub I. All right, and the idea is that I want to put bars, so this is X plus or minus some confidence interval. And the idea here is that at some probability level, I expect true mean to fall within between my confidence intervals at some desired level. So for example, 95% of the time. 95% of the time, my true mean will be within these confidence intervals of my sample mean. All right, so this gives me some idea. I go out and measure a sample mean. I want to know what the true mean is. I can calculate these confidence intervals. All right, so the confidence interval I can use the t distribution is equal to this critical t value. We'll talk about how we calculate this, t df times the standard error of the mean. All right, and t crit, this t star df, is the critical t value for a desired level. And by this, I mean like 95%, all right? All right, and it's a function of the degrees of freedom DOF. All right, and the degrees of freedom are basically the number of samples minus 1 for the number of parameters, which is the mean. All right, and at the end of the day, what this t value, it gives me the number of standard deviations away, all right, my confidence interval. So 95% might be, for example, 1.7 standard deviations away from my sample mean. All right, and this is just a function of the t distribution, which we've assumed our mean follows. All right. And if we multiply that by the standard error, we'll get our confidence intervals. All right, so all this is really doing is figuring out how far out we want to draw the line, all right, in order to be at 95% of the time, we're going to expect our true mean to fall within our within these levels of our sample mean. All right, so we can calculate t star df can be found using a lookup table, or we're going to use Python. All right, and to do that, we're going to use a function called, we're going to import a function from SciPy. So we need to import SciPy. All right, and we can find our t critical so this is just code. I can't write t star. So my critical t value is a function SciPy dot stats dot t for the t function dot ppf. All right, this is just something to do with the probability distribution for the t function. The quantile is 1 minus the level I want. So for example, for the 95th percentile, it would be 1 minus 0.95 over 2. All right, so this is the 95th percentile. And degrees of freedom, df, is equal to n minus 1, where n is the number of samples. So this is going to return this value, t star, And then I can calculate my confidence interval using this equation. So I need to first calculate the standard error of the mean. Then I calculate the critical t-value. I multiply those and I'm going to get my confidence interval. And now I can write my mean, the real value of the mean should fall between how do I want to, we're going to call this the true value of the mean, x bar prime, should be equal to my sample mean plus or minus t crit times my standard error of the mean. All right, so this is our basic idea of forecasting or using our uncertainty of the mean to think about what the true value of the mean is and what the error bars are. All right, so we can calculate. Python easily calculates an average value of a sample. That's what it does. And this is a way for us to put error bars on that and say we think the true value falls in between these values. So for the 95th percentile, which we need to do in the homework, that would be 0.95/2. Okay, so that's the standard error of the mean. And the basic idea is that we don't know what the true mean is. We get a sample mean, and so we want to figure out how uncertain we are on the real population mean. So now let's talk about model forecast error. So in science, we're going to do this all the time. We're going to try and we'll get asked to predict, well, what's the annual flow in the Lochsa going to be next year? All right. And the farmers want to know this, the water managers want to know this. Everybody wants to know how much the annual discharge is. And so as a scientist, our first thing we're going to do is figure out some way to model or predict the flow. And what I want to talk about right now is thinking about what that model forecast error is. So the simplest model, this is a statistical model, but it just says, hey, most of the time, you know, if I have most of the time, I expect that my observed value should be close to the expected value or the highest probability value, right? And so that means we can use the sample mean as a model. And this says that the predicted value should be equal to my sample mean. All right, so predicted value equal to the sample to the mean value. This just says, you know, the most probable value is the mean. All right, but we are uncertain both in we don't know what the true mean is, All right, so we have uncertainty there. And also we know that there's spread. Not every year does the flow equal to the average flow, you know, and so there are lower probability events that are farther away. All right, and we can characterize that with the distribution of the values from the mean. So first of all, let's define the standard error of the model. And I'm going to call this SM squared. All right, this is the variance of the model, basically, or the variance of the model error, truly is what it is. So this is the standard error squared. This first equation is the standard error of the model squared, SM squared. And this, we can just say that the variance of the model error is equal to the sum for all observations of the flow that year, the observed flow that year, minus the modeled, which is y bar. And we're going to square these. And we're going to divide this by n over 1, the number of observations. All right, so then the standard error is just the square root of the standard error squared. And so this is equal to square root 1 over n minus 1. I'm just rearrange this a little bit. Okay, so I can figure out the standard error of the model by calculating, taking all my observations, say 20 observations, subtracting the mean from that, squaring it, dividing it by n minus 1, and taking the square root of that total value. This gives me the standard error of the model. And you can think about this as like, what is the average error? Or how, on average, how wrong is my model? All right, so this is the error of the model. Ugh. All right, how bad is my model? All right, if I don't have, if my values are always very close to my average value, then I don't have much error in my model. All right, so that's the error of the model. The other source of error is the fact that I don't really know what y bar is. I don't know what I don't really know the parameter. All right. Well, this is equal to my standard error of the model from up above. sorry, of the mean. Right, and this is the sample standard deviation over the number of samples. So I have two sources of error in my forecast. One, the model's wrong, and two, I don't really even know the model, right? So when I want to figure out what the uncertainty is in my forecast, has to include, my error of my forecast has to include both of these uncertainties. The fact that my model's wrong, one, and the fact that I don't really know what the model is, two. And so I have to include those. So let's calculate the standard error of the forecast, SEF, which is the standard error of the forecast. And this is equal to, if I want to combine errors, I usually end up doing this. I take a square root of the errors squared. So this would be the standard error of the model, SM squared, which is this equation right here. All right. Plus the standard error of the mean squared, which is just the square of this equation right here. All right, this is my forecast mean. Now, I can use this same confidence interval calculation that I used for my putting error bars on my mean. I assume this follows the t-distribution. All right, and I can write the confidence intervals. C sub I is equal to T star DF, all right, times SE forecast, all right? Instead of the standard error of the mean alone, it is now the standard error of the forecast, which includes both the error of the model and the error of the mean, all right? And again, this is for a given confidence level. So for a confidence level, say 95th percent, and degrees of freedom. All right, so we use the exact same stats call. So in Python, my critical t-value is scipy dot stats dot t dot ppf. All right, this returns my t-crit function. 1 minus 0.95 over 2 for the 95th confidence level. All right, or the 95% confidence level. df equals to n minus 1. And then I can say, you know, my predicted discharge is equal to the sample mean discharge plus minus T df star times SEF, right? And this will be a number. And I would expect that 95% of the time, the observed value or the observed value of discharge will fall within these two values from my sample mean. All right, so that's gives you enough theory to think about how we implement this in Python. The basic idea is that we have two sources of uncertainty. We don't know what the true mean is. All right, so we've talked about how we calculate the standard error of the mean and the confidence intervals on the mean. All right. And then if we want to think about modeled or forecasted error, we need to think about the error of the model. All right, the fact that the model is not correct. And we need to think about the error of the model parameters or the model itself. So we don't really know what the model is, the standard error of the mean. We combine those two into the standard error of the forecast. We assume that the difference between the observed and or the difference between the true and the sample forecast follows a t-distribution, and we can calculate the critical t values for those for a given confidence level and multiply that by the standard error. All right, this is just enough stats to make you dangerous, but I hope it gives you some introduction into random variables, model uncertainty, and how we calculate model uncertainty. It is the theory behind the third part of your homework. And really the rest of it is just grabbing the right values, calculating sample means, calculating sample standard deviations, calculating the difference between the observed value and the mean, and calculating the correct t-critical values. I hope you all have a good day. Have fun working on your homework assignments. Boone will be there to help you with your homework assignments. And I will see you guys Tuesday. Feel free to ask questions in the forum. Talk to you later. Bye.